All right, this time around we want to get into talking about parameters and communication between functions, so between the caller and the callee. You need some way to tell the callee what kind of information you want it to process, and possibly some way for it to get results back to the caller. So there's three typical ways of doing that. You can either use registers, right? If you've got a set of actual registers that you can stick values in and they can both look at, so you can share information that way. You can use some kind of fixed memory locations and say, okay, well, go look here, and that's where the data is. Or you can use parameter passing and the call stack approach, which is, of course, the most common one that we'll wind up taking a look at. Just in terms of the mechanics of things, if you're using registers, right, you've got a finite number of them. So if you're trying to do something like recursion, you've got a finite number of spaces that you can use to communicate between caller and callee, and then the function they call, and then the function they call. And so you have a sort of hard limit on the recursion depth that you can get into, and simply on the amount of data you can pass, period. If you're passing through fixed locations in memory, you've got a similar issue, right? Both the caller and the callee have to know which chunks of memory to look in. And so if you're using hard-coded values, then you're essentially back to the same problem as you've got with registers. One of the things that you could do is kind of emulate your own little runtime stack if there's not one built in, where you go in and say, okay, well, what we'll do is have maybe one memory location that tells the caller or tells the callee where the top of the stack is, and maybe a second fixed memory location that tells it how many parameters have been passed. And then it can go through and just manually push information onto this manual stack, if you like, and pop information off. So you could, even if there wasn't an existing runtime stack that stored parameter information, you could do it yourself if you ever needed to. But again, typically we're looking at this idea of a runtime stack where every function call involves a stack frame that's got space that you can have local variables, you can have parameters, you can have return values, that kind of thing. So again, that's the typical approach, just because it does give it a nice, easy approach to supporting generalized recursion. Okay, so I'm going to kind of go forward from this point, assuming we're looking at a runtime stack approach. Even within that, we've got a huge variety of different styles of parameter passing mechanisms that you can use. So some of the ones that we're going to talk about are pass by value, which of course you're all familiar with, pass by reference, again, you're all familiar with. Passing by value return is a little different, so we'll talk about that. By result and by name are also a little different than things you might have seen typically. So we'll spend some time talking about those. And of course, some of the things that we looked at specifically with our Lisp studies earlier in the term, the idea of having keyword parameter passing instead of the traditional positional passing. The ideas of being able to pass optional parameters with default values, the ability to pass functions with arbitrary numbers of parameters, right, the variadic functions, and of course that'll be the topic we get into for Lab 9 as well. So those are all things that we'll talk about a bit today. We'll look at overloading functions, right, the idea of having a single function name, but a bunch of different implementations with possibly different parameter lists or different types of parameters. And maybe we've got a print date function where we can call it passing it an integer representation, or we can pass it using a string representation, or we can call it using a string representation. So different ideas for having one name for a bunch of similar functions. Or the idea of generic functions, right? That is sort of the templated idea that we've looked at in C++, where your function is able to accept a variety of different data types. Essentially, you're providing a template. Here's what the function would look like if we knew what the data type was, and it's up to the compiler or the interpreter to go through and say, you're going to call it with an int. I'll create an int version of this. So I'll fill in the template with int as the data type. So we'll spend some time talking about each of these things. So I wanted to talk about the passing mechanisms first. And the idea is pass by value you're familiar with. You make a copy of whatever's being passed and either put it on the stack, right, in the parameter passing space, or you put it somewhere off in the heap, allocate space in the heap, and stick a reference to it on the stack with some kind of a provision saying that essentially, or I guess if you're making a copy and putting it in the heap, you know that you've got a duplicate of the value. There's no possibility of altering the original. The notion of passing by reference, where either explicitly or implicitly we've got the memory address of the item being referred to. And of course, this allows us to pass much more quickly because we're not actually duplicating the entire thing. We're just saying, okay, well, let's look up the address, push it on the stack, and let it go from there. So it's faster. You're not trying to make an entire copy of what might be a large item. You're not using the memory space that's going to require. But you're introducing the possibility that since the callee has got a reference to the original item, you might have side effects taking place. Right? The callee might be able to alter whatever it was it's being referred to. And that might be what you want, right? You actually want pass by reference, or it might be something that you would prefer to avoid. You don't want the possibility of the callee corrupting your data. By value return is a little different. So it's pass by value. So you copy the item to the stack, but the function can return the resulting value of the item. So essentially the function can change the copy it's given and give back that revised version, which can then be copied into your original variable. So it's kind of like pass by reference in terms of the ability to have side effects, but it's like pass by value in the sense that you're putting everything on the stack and copying everything back and forth. So this one is far more rare, but it is a possibility. The idea of by result is kind of like the last half of a by value return, where you're saying, here's the variable I want filled in, and then the function is going off and doing whatever it's going to do and sticking the value in that location. So it can either be this idea of the function copies the stuff into the space on the stack and it gets copied back, or it can be sort of a reference idea. Again, these two are certainly far less common. And then the last one, by name, is a little different, a little interesting. It's, in a way you can think of it similar to the idea of dynamic scoping. What we're going to do is instead of passing an actual variable, we're going to pass a variable name, where we're going to say, when you run, use the name X, and whatever variable is in scope for you with the name X, use that when you run. So it's providing a very different way. When you call the function, it is going to kind of depend dynamically on what that function has access to. So a very different approach. There are a handful of languages. I think Snowball is one, if I remember correctly, that support this kind of a mechanism. It does involve thinking about your coding very differently if you're going to start using these. All right, in terms of some of the parameter passing options that we mentioned, again, we've looked at this in Lisp, having optional parameters, right? Parameters with default values. So if the caller doesn't supply the optional parameters, then the callee just fills them in with the default value. And of course, you've seen how to do this in C++. You've seen how to do this in Lisp now. The keyword versus positional parameter passing, right? Most of the languages that we've looked at have used positional parameter passing, right? It's far and away the most common, where the first thing the caller passes goes to the first of the parameters in the callee. The second goes to the second, the third goes to the third, etc. But we looked at this idea of having keyword passing in Lisp, where you can say, here's the value I want to go to parameter X. Here's the parameter, or here's the value I want to go to parameter Y. And you can pass them in any order since you're actually saying, here's the names of the things I want them to be assigned to. So, very different approach. Totally valid, not that widely supported because it does still mean that the developer has to know the names of the parameters in the targeted function in the callee. And then the last one was the idea of variadic functions. Right? You've seen this with the and rest in Lisp, the idea that you can pass an arbitrary number of parameters to a function. You can pass 1, you can pass 500. And the function will have some mechanism of finding out how many you passed and of actually getting at each of these. So in Lab 9, we're going to go through and we're actually going to do this in C and in C++. So there's a macro package that we can use in C to do this. And it's the kind of thing that's done for printfs and scanfs where you can already pass, any number of parameters that you want to use. So we'll take a look at how you can do that in C. And we'll take a look at how you can do that with templates or templated functions in C++. So those will be the two parts that we'll look at for Lab 9. All right, in terms of overloading functions, again, the idea you've hopefully played with this in C++ or other languages, the idea that you can have a bunch of different implementations of a function where they've all got the same name, but they take different parameter lists. So the compiler knows which one you actually want to call based on the types of parameters that you pass, the order that they're in, the number of parameters that you pass. So it can go through and say, you're passing a string, you want the string version of this function. You're passing an int, a float, and a char, you want that version of the function. So it does mean that the compiler has to be able to tell for any call that you can make which function, which implementation of the function should be called. And so if you've got overlap between the different data types, so let's say we've got one version of function f that takes ints and another version of the function that takes longs, and you pass 3, obviously that's sort of type compatible with either one of those. Which one should the compiler use? Or if you've got functions that have some optional parameters, so you've got one version of a function that takes a parameter x and another version that takes, say x is an int, and another one that takes an int and then an optional char. If you just pass 3 or a 10 or something like that, how does it know which one to use? Do you want the one that's just an int, or do you want the one that's an int with the optional value, the default value for the char? So it does make it more complicated, and a couple of possibilities arise there. Your compiler could go through and decide that it's going to look at the calls that you make at compile time and decide then and there, this is ambiguous, I'm not going to compile, I'm going to generate a warning or an error or whatever it might be. Or we'll just defer it and wait until runtime, and if it's executing and we hit an ambiguous call, then we'll generate an error or a warning at that time. And another possibility here at compile time is to go through and say, well, what if we just looked at the data types for the functions that your overloaded functions, and if there's any overlap at all between them, if there's any possibility that you could make an ambiguous call, regardless of whether or not your code actually does, then we'll say, oh, nope, that's a warning or that's an error. And that's actually the approach that's taken in the sort of C++ style, where it looks at your parameter lists, and if it sees any overlap, it says, oh, no, you can't do that. And it makes sense when you think of things from the point of view of separate compilation, where you don't know at compile time what's happening in other object files, other .o files. They might be making invalid calls. You don't know that, so you're just going to say, nope, you're trying to define a set of ambiguous functions. I'm not going to let you do that. So those are all things that need to be considered if your language is going to support function overloading. And if you're using a language that supports function overloading, you have to know which way it's doing this. All right, and then the last topic I wanted to get into along these lines is the idea of generic functions or templated functions. The notion that we've got one implementation of a function, but it can take a whole bunch of different data types for specific parameters. So we've played with templated C++ functions. The idea is you essentially provide a variable as your data type. You provide a skeleton or a template for the implementation of the function, and the compiler looks at the actual calls to the function and says, you're calling this function with an int, so I'm going to fill in the template using int in place of that variable type, or using float or char or whatever it is that you actually call it with. So in this case, typically the idea with compiled languages is that it's got to be done at compile time, so it's got to know what types are being used when it compiles that function. So it's got to go through and say, I have to build an int version of this and a float version of this and a char version of this. If it's an interpreted language, then maybe it's possible that you wait until runtime, and when you actually hit a call, at that point you sort of pause execution briefly if you haven't already built a version of this for ints or floats or whatever it might be, generate the right version of the function and run it then. So there are possibilities each way. It is something to think about. And as you've probably seen by this point, it does raise issues with separate compilation. I usually annoy you with this in things like the 265 class, where we look at the idea that we've got the definition of our templated function in one file that gets compiled, and we've got the uses of it in other files that get separately compiled, and they all get linked together at the end. Well, when the compiler goes through and does that one file that's got the templated function in it, it doesn't know what data types are being used in the other files. And so it doesn't know which versions of this function it should actually build. So a couple of possibilities there. You can either put the template for your function in a header file that just gets included with everybody else, so all those other files know how to fill in the template, know how to build the template, and when they get compiled, the compiler builds versions of it there. Or another possibility is in the file, either let's say the header file or the C++ file, the CPP file, the source code file that's got the template definition in it, you add additional instructions telling the compiler specifically, okay, I want you to build one of these with strings, I want you to build one of these with floats, I want you to build one of these with chars. But again, the separate compilation is an issue to be considered when you're looking at this idea of sort of generic functions. All right, we'll leave the parameter passing there, see what we can come up with next time.